Hello, my fellow chemists. In this video, we're going to take a look at trends in the periodic table. This is labeled as an intermediate video because it assumes you have a basic understanding of atomic structure. If you need a review on the topics, I will have a link in the upper right-hand corner. So let's get started. The main trends that we're going to take a look at are atomic size, also called atomic radius, ionization energy, electronegativity, and valence electrons. So if we start off by looking at atomic size, I'll just circle francium down here and fluorine up here, just kind of as a basis to guide us on. As you go diagonally across and down the periodic table, the size of atoms increases. So what that means is elements down where francium are have a very large size, and elements up where fluorine are have a very small size. We'll put a little table up here to list that. So if a chemist, a professor asked you a question and said, well, if you're taking a look at, say, oxygen, zinc, and osmium, and asked which of those three elements is the largest, all you have to do is say, well, osmium is the closest to the bottom left-hand corner, so it must be the largest. And oxygen is closest to the upper right-hand corner, so it must be the smallest. The second trend that we're going to take a look at is ionization energy. And ionization energy is the ability of the least tightly bound electron to be pulled out of an atom. And if we take a look, the ionization energy increases as you go diagonally across and up the periodic table. So the ionization energy will increase as you go diagonally across and up. So elements around where fluorine are have a very high ionization energy. And elements down near where francium are have a very low ionization energy. Now let's take a look at the forces felt on atoms based on their size to see if we can explain why an element like francium has a low ionization energy and an element like fluorine would have a high ionization energy. Now remember, francium is a large element, large in size, so it would be represented by this third green ring out here, because that's pretty far away from the nucleus. That would be a large atom. The force that electrons feel on them from the protons in the nucleus is directly dependent upon how far those electrons are away from the nucleus. So if you have a large atom, the valence electrons are pretty far away from the protons in the nucleus. So therefore, they're going to feel a very weak pull on them from the nucleus, which means one of the electrons in the valence shell in a large atom can very easily be pulled out or pulled away from that atom. Whereas if we take a look at a small element like fluorine, kind of represented by this small green ring in here close to the nucleus, even the valence electrons in a small atom are pretty close to the nucleus. So they feel a very strong electromagnetic pull by the protons. So it is very hard to pull a valence electron in a small element away from it. So that's why small elements have a very high ionization energy. It takes a lot of energy to pull a valence electron away from them. And large elements have a very low ionization energy. Very easy to pull a valence electron out of them. If we take a look at the third trend, electronegativity, Electronegativity is just the ability of an atom to pull electrons towards itself. And the trend for electronegativity is as you go diagonally across and up the periodic table, the electronegativity increases. So the element fluorine actually has the highest electronegativity. So elements up near fluorine have a very high electronegativity. And there is an exception to this. All the elements that are noble gases that are in group 18, they really don't have any electronegativity at all because their outermost energy level is filled with 8 electrons. Their octet is filled, so they have no desire to pull more electrons in towards them. So the highest electronegativity is actually felt by fluorine and the halogens. And then if we go diagonally across and down, elements near where francium are, they have a very low electronegativity. And then let's use this model of our atom again to kind of explain why. If you have a large atom, kind of represented again by this third green circle, and a new electron was to be added into that atom, it would feel very little pull on it from the nucleus because it's so far away from the nucleus. So that atom in general has a very low desire or low ability to pull in new electrons. Whereas if you're looking at a very small atom like fluorine, represented by this first circle here, a new electron that would come in, even though it's a valence electron, it's still relatively close to the nucleus, so it's going to feel a very strong pull by the protons in the nucleus. So small atoms will have a very high electronegativity, whereas large atoms have a very low electronegativity. And then if we take a look at the last trend, which is valence electrons, you can tell how many valence electrons an atom has based on the group that it belongs to. Elements that are in group 1 have one valence electron. So all these elements in group 1 have one valence electron. Elements in group 2 have two valence electrons. And then for now, we're just going to skip all the transition metals. Elements in group 13 have 3 valence electrons. Elements in group 14 have 4 valence electrons. Elements in group 15 have 5. Elements in group 16 have 6 valence electrons. Elements in group 17 have 7 valence electrons. And the noble gases, as we mentioned earlier, that's group 18, they have 8 valence electrons. So as long as you know the groups of the periodic table, you know how many valence electrons all of the atoms in that group has. Now, the transition metals, which is basically groups 3 through 12, they have either 1 or 2 valence electrons, but usually it's 2. That's it for this lesson. I hope you learned something. If you did, make sure you subscribe and like, and I'll see you in the next video.